Welcome to homework.
Okay, first of all, I'll just let you know that the answer is going to be selenium hexafluoride. This is the answer. Uh, and now we can go through and, you know, discuss more than that. Okay, so let's step through what the geometry is of each of these. Okay, uh, IF4 plus, how would we know? Well, we know we're going to put the iodine as being central because it's the least electronegative, right? So we're going to have an iodine with 4 bonds to fluorine. Okay. And then, it can be useful to figure out how many electrons we have to work with. Once we've built the skeleton, we're going to get 7 from iodine because it's in group 7A. Fluorine is also in group 7A, but we've got 4 of them, so we're going to get 4 times 7. So I am seeing 35 electrons, but then remember that's got a positive charge, so we got to subtract 1, so that's a total of 34 electrons. Okay, we also know that halogens, like fluorine, want to have a single bond and the rest as lone pairs, so we can go ahead and apply lone pairs all around here. And we know that iodine is a very large molecule, so it can accommodate more than a full octet. It can have an expanded octet. And if you weren't aware, each of these sets with a single bond and 3 lone pairs consumes 8 electrons. And if we do that 4 times, then we've used 32 electrons. Okay, which leaves us with 2 electrons left over, which would be a lone pair on iodine. So now, to figure out the electron pair geometry, we simply count the number of regions of electron density around iodine. That would be any bond counts as a region, and any lone pair counts as a region. And we see 5 electron regions. And for an octahedral electron pair geometry, we need to have 6 electron regions. That's the magic number. We don't have that here, so we know that this is not octahedral electron pair geometry. And we just go through and do that with the rest of these. So like phosphorus with 6 bonds to chlorine. I'm going to, not do the whole entire thing every time, right? And then we can kind of figure out how many electrons we have to work with. We get 5 from phosphorus. We get 6 times 7. We get 42 from chlorine. And then we have a negative charge, right? So that's 48 in total. And we got all our lone pairs. So we got all our lone pairs. And luckily, 6 times 8. Recall that each chlorine with its single bond and 3 lone pairs gives us 8 electrons. 6 times 8 is exactly 48. Okay. Oh, look at that. I was wrong. Yeah, BCl6 is also. So the answer is selenium hexafluoride as well as PCl6 minus. That helps to actually do the problem. Okay, now let's do selenium hexafluoride. Now I'm starting to wonder, maybe I'm wrong about selenium hexafluoride. So selenium, check what group it's in. Selenium is in group, so it's beneath sulfur, so it's 6A. So we know that selenium is going to be the central atom. We know we're going to have 6 bonds to fluorine. And in terms of electrons, we're going to get 6 from selenium because it's in group A, plus 6 times 7 from the fluorines, right? And that's going to be a total of 48 electrons. And we already know that each of these is worth 8. And there's 6 of them. 6 times 8 is 48. So this is good, right? We have, in terms of electron regions, we've got 1, 2, 3, 4, 5, 6. That's the magic number for tetrahedral. All right, next is tin chloride, tin 4 chloride, as it would be. We look at tin, that's in group 4. Great. And so we get 4 electrons from tin plus 4 times 7 from chlorine. That's going to give us 32 total. And each bond to chlorine and with its 3 lone pairs is worth 8. 8 times 4 equals 32. So this is all good. There's no extra lone pairs anywhere. And we only have 4 electron regions, which is not equal to 6. So this is not tetrahedral. And xenon tetrafluoride. Right. Okay, so we're going to get 8 electrons from xenon, and then we're going to have 4 times 7 electrons from fluorine, and that's going to equal what? 28 plus 8 is 36. Oh, this looks like it's going to be octahedral as well. Right, because each of these fluorines is going to be 8. And we've used up 32 from the fluorine, which gives us 4 electrons remaining. Those will be lone pairs on the xenon. And yeah, this will be 6 electron regions as well. That's tetrahedral, TH for short. Cool. So the final answer then would be phosphorus hexafluoride minus selenium hexafluoride and xenon tetrafluoride.